Yeah. Okay. So we can now start the session. Okay. So this is your first question. Try to solve it. Okay. After 5 minutes, I will solve it for you.
Sir, it's a revision session or a question paper solving session?
It is a question paper solving session. The revision session has been shifted on Thursday and Friday.
Okay.
But sir, I see mail like it is a revision session only, like WhatsApp messages.
It was a revision session, but it has been shifted on Thursday. Okay.
Oh, now it's been on Thursday, so we'll
Yeah.
get the message, right? Timing and all.
Uh, yeah. See, timing will be same. Okay. On Thursday there was
Same.
one PYQ session, and that has been shifted to today. Okay.
Okay. All right. Thank you. So this is what session today? Like this session is for
Old
what?
PYQ. Old PYQ. We are going to
Okay.
solve the
Old.
September 22 quiz to paper of maths book.
Uh,
Okay.
Okay.
Pulkit, are you getting like a notification to admit the people?
No. No.
Okay, okay. No, you will be because because you are the this is the older link. You will get that here.
No, this is the older link for, yeah, I know that you have created the doubt session link, right? The doubt
Yes,
session.
yes. This is the doubt session
And
link. Yes.
in that session, in that also I told you that I was not the host.
So usually people used to join, so I don't think there is any issue. Yeah, this is a maths two session, so very less people. Okay, no issues.
Yeah.
Yeah, continue with that. Pulkit.
Can you paste the link of question paper in chat? Can you paste the link of question paper in chat?
What are you saying?
No, no, this question paper link in chat.
A question. Okay, I will send it.
So are we going to discuss this paper?
Yes. Okay. I am giving you some time. Till then, you should try by yourself for this question. After that, I will solve it. Okay. So are you all done with this question, or you guys need more time to solve it? Hello.
We can go proceed, sir.
Okay. Okay.
Sir, which question are we solving? Sorry.
This is the first question. Okay.
Sir, which one is the first question? Sorry, I see four, five questions.
Okay. Okay. This is your question, that which of the following options are true? It is a multiple select question, and you
Oh,
have given these four options. Okay.
okay. Sure, thanks.
Is this the first question we're starting with?
Yeah. This is the first question of this QP set. Okay.
Okay.
So first option is correct, right?
Let everybody solve it. Okay. After that, we will discuss it. So, should we move towards solution part?
Yes, please.
So, if you see the first option, it is saying every matrix is similar to itself. Yeah. So, what about this statement? Is this correct or not?
Yes, if you
Correct.
take PSI.
Yes, correct.
It's correct, right? Because it's come from the property itself that if B is similar to, okay, P inverse BP. So if you take P to be your identity matrix, then you will get B is similar to B, right? So this is in the property also. Now, what about the second option? If A is similar to B, then
Yeah,
A inverse is similar to B inverse,
yeah,
right?
yeah. This is also
It is
Yeah.
true.
also correct, sir.
True.
If we take, right, P inverse AP, if you take inverse both sides, then what will you get? B inverse is equal to, it will be P A inverse P inverse. Okay, got it?
Yes.
Hmm. Now, any doubt in these two options?
Sir, how did you open this right hand side in taking whole inverse? Because
Actually,
A B whole inverse is B inverse A inverse.
yeah, AB whole inverse is equal to B inverse. Oh, yeah, let's say you are correct. So it will be P, okay. Oh, sorry. Yeah, yeah. See, if you are going to open it, then only the P inverse and P will get shifted. Okay, this will
How,
get
sir?
shifted. And
Could you explain it in detail?
uh, see, just as you said, if you do AB inverse, you will get B inverse, A
A
inverse,
inverse.
right? So
Right.
if you are going to do it for like triplet of it, then you will get this. Okay, it comes from the property.
So which is, for example, I have a inverse ABC. What will be
Hmm. Then
ABC
it will
whole
be
inverse?
then it will be C inverse, A inverse, and B inverse, or ABC inverse. Okay, it will be C inverse, A inverse, B inverse. Sorry, I wrote it right.
The C inverse, B inverse, and A inverse, right?
ABA.
Yeah, sorry. It will be C inverse,
B
B
inverse
will
and
be
A inverse.
A inverse.
Okay, just in reverse
Yeah,
order,
yeah.
basically.
Okay.
Okay, we got it,
Hmm.
got it. Thank you.
Hmm. Now for third option. Okay.
So,
If yeah, any doubt?
no.
Hmm. Okay. If you see this matrix clearly, this is a scalar matrix, right? And we know that a scalar matrix is only similar to itself. So it will not, and this matrix is not the same as this matrix. So this option will be correct. Oh, sorry, incorrect.
Okay, but
Okay.
the prima facie, if we see like rank is also same, trace is also same, and determinant is also same, right?
Yeah, yeah. But
Still, this
see,
is not
we know
similar,
that,
right?
yeah, yeah. We know that by making these all three to be same does not imply that it will be a similar matrix, right?
Okay.
Hmm.
So what is
So
basically
like,
physical meaning of similar? I mean, is that a multiple of or scaling of that
They are
vector?
see, they are coming from the same linear transformation by taking a same basis for domain and codomain.
Okay.
Okay.
so means is so it's for always like scalar matrix are always similar to itself only.
Yeah. See, I we can prove it also here. Like
Okay.
if B is equal to P inverse AP, okay, and A is your if your A is your scalar matrix, then we can write A as P inverse alpha times I, right? Where alpha is some scalar,
Yes. Hmm.
and then we can take this alpha out. Okay, then it will be P inverse. Identity times P inverse will be P inverse, and it will be P. So you'll get alpha
Again,
time
it's the
identity,
identity matrix. Yes.
which is nothing but just your A, right? So a scalar matrix is only similar to itself.
Okay.
Hmm. Now fourth option. If A is similar to B plus C, then rank of A is equal to rank of B plus rank of C.
No, it won't be.
So what are your thoughts about it?
It won't be. It will be rank of B plus C, but it's not equal to rank
Yeah,
of B plus rank of C. It will be less than that.
yeah, yeah, it will not be equal. See, what if all the three has same rank? Okay, let's suppose your ABC comes from a 2 cross 2 matrix. Okay, and if A is similar to B plus C, B plus C will also be our 2 cross 2 matrix. And if both of them have same rank, because similarity means same rank, so rank of A will be 2, while rank of B plus rank of C will become 4. Okay, which will not be
Yes.
equal.
So it cannot be equal. Yes.
For
But
example, yeah,
no, no, please, sorry, please go on.
for example, if you take A to be your uh, okay, uh,
Can we take an example on 3 by 3
yeah,
if it has to be proved like
okay, 3
rank
by
system?
3.
You can go at it with the property also, right? Rank of A plus B is less than rank of A plus rank of B.
If you want the example for 3 cross 3, then you can take A to be your, let's say this, okay, and if you are gonna take mm, I am taking just a simple basic example so that you can understand. Okay. So if you see, the rank of B and C are 2 and rank of A is also 2, right? All three matrices have same rank. And B plus C, you will get identity matrix. So B plus C matrix is similar to A, which is also an identity matrix. So, but here the rank of B plus rank of C will be 4. Oh, I mean here it will be 6, while rank of A is 3. So this option will not be true, right?
How the
What is
rank of A, B plus C will be 6?
rank of B plus rank of C? Rank of B is what? 3.
Yes,
Yes. What is the rank of C? 3.
3. 3.
So 3 plus 3, 6.
No, but if you look at the matrix that you will arrive at from B plus C, it will be 1, 0, 0. It will be the same matrix as A. So the,
3.
the rank of that matrix will be 3.
Yeah. No. I am talking about this condition. Okay. What is the rank of A we got here? 3. What is the rank of B? 3. Rank of C? 3. So 3 plus 3 is 6, which is not equal to 3. Now, yeah, the rank of, if you are asking for rank of B plus C, that will be 3. But rank of B plus rank of C, that will be 6.
Okay, okay.
Okay.
In that way, yeah. Okay, fine. Yeah, thanks.
So here,
So
For
this option will
similarity
be,
condition, the rank has to be same, right?
yeah, the rank of A will be same as the rank of B plus C.
And if that holds good for any matrix, two matrices, then we can say they are similar matrices, right?
No, by only rank to be same, we can't say similar matrix. This case only holds for equivalence matrix. Okay. For equivalence, we just need to check the order and the rank. But for similar, first check the rank, determinant, and trace. But even after these three to be same, we can't say that they are similar matrix. Okay.
Then how are we concluding here?
For for fourth option, I have just taken one example to deny it.
If you please both note down where you
Okay. Yeah.
about this question. Yeah.
Hmm.
Okay.
Yeah. See, it is saying that rank if a matrix A is similar to the matrix B plus C. You know what is the matrix you will get after B plus C?
That
Identity.
is identity matrix as a one only. Yeah.
Yeah. And A is also identity, so it will be similar.
Okay.
Then the condition they are stating that the rank of A, which is 3,
Hmm.
okay, it will be the same as the rank of B plus rank of C. But rank of B is 3, rank of C is 3, so 3 plus 3 is 6, and rank of A is 3, which is not equal to 6, right?
Okay. So they were basically trying to compare on the one aspect of the similarity, which was rank and the other thing, right? So which is why you said, okay, fine, this is the answer.
They are not like checking if A will be similar to B. They are saying like A is similar to B plus C matrix, okay? Then rank of A will be equal to rank of B plus rank of C. This is the condition that we are checking,
Okay.
not a
Okay.
similarity condition.
Okay. Okay. Yeah, we can go ahead. Thanks.
sir, if you explain the similarity matrix, how will check that will be helpful.
Uh, First, you should check the determinant, trace, and rank. Okay, these three are the conditions. Now, if all three will comes out to be same, then you have to go by definition, which is PB equal to AP. Okay.
So space is like equal in equivalent matrix as well, or only in similar matrix?
No, see, in equivalence matrix, we just need to check the what is this?
Rank and determinant.
Rank.
That's it.
No, see, rank only we need to check. Okay,
Okay.
determinant not only rank.
Okay. And in similar matrix, we can check the determinant, trace, and rank.
We need to check all three, but even if all three are same, we can't say that they are similar.
Yes.
Okay,
That I understand.
after
Thank you.
then we have to go by this definition.
Then we, in this case, we need to find a matrix P such that P inverse into a P that condition also we need to check.
Yeah. Okay.
So there will be multiple cases in that case.
Yeah, because these will not be unique. P
Correct.
can be in many methods. Okay.
Any easier or anything will
What?
so there will be multiple cases, na, in that case.
Yeah.
So return trial method will try fix it.
Yeah, you have to choose one P for which will be invertible. Okay, you just need to remember
Okay.
that condition. You have to take invertible P. If even if you are able to find one P, that will be enough. Okay. So
Sir,
yeah,
sir, identity matrix is similar to every scalar matrix.
no, identity matrix is only similar to itself. Okay,
Okay. Sir,
because identity
mhm,
matrix is also a scalar matrix, right? And
yes,
as I
sir.
told, a scalar matrix is only similar to itself.
Okay.
Okay, so I have one doubt. Can I ask?
Yeah.
Yeah. So actually, suppose two matrices are given and the determinants of both the matrices is zero. Can they be equivalent?
No, not necessary.
Not right. But in the
Yeah.
activity questions, like there's a question, both determinant is zero. The determinant of both the matrices is zero, but still the like in option it's
Are
like it's showing correct.
are the matrices given?
Yes, matrices are given, and
Then
the
no, I
determinant is
you have to find the rank of the matrix. Okay, their rank must be coming out to be equal. That's why they are given equivalence.
okay.
Okay.
Means if the determinant is zero, still if the rank is same, then the matrices are equivalent, right?
Yeah, because if determinant is zero, then it will not have full rank. The matrices, it will have the
Huh.
rank less than the order, right?
Yes. Okay, means it can be equivalent. Okay.
Sir, you said that scalar matrix is only similar to itself, right? But in the first option, every matrix is similar to itself. So
Yeah.
once you are saying that every matrix is similar to itself, so scalar matrix will all automatically be similar to itself.
Yeah. See, every matrix is similar to itself, but scalar matrix is only similar to itself. That means there is no other such matrix which will be similar to a scalar matrix.
Okay, that means in non-scalar matrix, there can be possibility that multiple matrices can be similar
Yeah.
to that.
That's
Okay,
okay.
okay. Got it. Thank you.
Now, so this one is your next question. It is again a multiple select question. You have to choose which of the following options are true here. Shashi, can you mute yourself? Yeah, so should we move to our solution or you guys need more time?
Yes, sir,
Okay,
please.
go ahead.
Okay. The first statement, it is saying A is a non-zero matrix of order 4 cross 3 and rank of A is 3. Then the rows of A are linearly independent. Will it be true or false?
False.
False, right? Because you will have in the rows you will have 4 vectors in R3, right? 4 vectors in R3, and they can never be linearly independent. Okay, so this option will be incorrect. Now, second option, if A is a non-zero matrix of order 4 cross 3 and rank of A is 3, then the columns of A are linearly independent. What about this? Will this be incorrect or correct?
Correct.
Correct. Then.
Correct, right? Because
Sir,
the
can you
rank
explain
of
first option once
yeah,
again?
first option. Okay. See, A is your 4 cross 3 matrix and rank of A is 3. Okay. That means the row space will be formed by only 3 vectors. And if you see, if you
Yes.
are going to form a 4 cross 3 matrix, you will have 4 vectors in a row, right? Which will be in
Yes.
R3, 4 vectors in R3. And we know 4 vectors in R3 can never be linearly independent. Okay.
Sir, we
Now
can
here,
like it depends on how we write the vectors now. Like it can be three vectors from R4. Like if I write it down in column form.
it's a 4 cross 3 matrix. It's already given. So
Yeah,
that means 4 rows, 3 column, right?
yeah,
So
right.
so the row vectors, what will be the row vectors here? The rows of A will be in R3, right? And there will be 4 rows. So 4 vectors in R3.
Okay. If I say row wise, then I can say that there are four
Yeah.
vectors in R3. And if I say
That
column wise,
that
then
So the
okay,
matrix
see in
formation is
both
given
there are
4 by
both
3,
sides.
no?
Yeah.
4 rows
Okay.
and 3 columns.
Hmm.
like if I have four vectors in R3, like if I have three vectors in R4, then also if I get
Well, no, that not necessary. 3 vector in R4, that not necessary that they will be linearly independent or dependent. See, they are saying both the case. See, in first case, we have okay. Let me form a one matrix. Okay, 1, 2, 3, 4, 5, 6, 7, and okay. This is a 4 cross 3 matrix, right? Now, if you see the row vectors, there are 4 vectors in R3, right? 1, 2, 3. One vector is 1 comma 2 comma 3. Second vector is 4 comma 5 comma 6. Third vector is 7 comma 8 comma 9. Fourth vector is 10 comma 11 comma 12. Right?
okay,
So
okay,
you have 4 vectors in R3 and they can never be linearly independent. So this
okay,
option will be incorrect. And one thing you can also see, the rank of A is 3. That means the row space will only be spanned by 3 vectors, not 4 vectors. So from here also you can see that linearly they will not be linearly independent. Okay,
okay. And the for
that is
second
also the
option, can you
uh,
explain like this? Okay.
because the rank of A is 3, that means the column space will be spanned by 3 vectors and there are only
What
3
will
columns,
what will my column space represent? That
1 comma 4.
three vectors in R4, right?
Yeah,
Three
but
vectors in
here
R4.
because yeah,
Okay,
here because the rank of A is 3 that is given, so your vector in columns will be linearly independent. If it is given that rank of A is 2, then they will also not be linearly independent.
so if I
Okay.
the rank is three, then
They
like
will be linearly independent. Column
how
vector.
one row will be one row will be zero, right? If rank
The
is three.
column, say, it is taking the column vector. Okay. If
Sir,
you
it means in case if nullity is 0, then in that case the column vectors will be linearly independent.
nullity.
For example, the rank is 3, right? And
Yes.
rank plus nullity equals to number of columns. So nullity is equals to 0 because number of
Yeah.
columns is also 3, right?
Yeah.
So in column space, if nullity is equals to 0, then it means they are linearly independent. Can we say that?
Yeah, you can say that. Okay.
But
But see,
in the first option, the
Well, that
nullity
is
is,
in row case. That is row cases, not in
yeah,
column case. I'm asking
yeah,
only in column
see,
specific.
the rank will be different for rows
rank is
and
same.
columns,
Okay,
right?
see, the rank of matrix is same as the dimension of row space, same as the dimension of column space.
Yeah, that's what I'm asking now. So
Yeah.
how will we can say this is independent, right? One row
Okay.
is rank is 3, then we can say clearly say one
What are
row
the
will be
dimension
0.
of column space will comes out to be here? Okay, see, if rank is 3, that means, okay, let's say this matrix. Okay, after row reducing it, if rank is 3, that means the matrix after row reducing it, you will get like this.
Yeah,
Correct?
yeah,
Yeah. So, in how many columns there are pivot element?
3
Three
columns.
columns.
So 3 will be your dimension of column space. That means all these three vectors 1, 4, 7, 10, 2, 5, 8, 11, 3, 6, 9, 12 will form your column space. Okay, the span of these three. And that means these three will be linearly independent. Okay. See,
Uh,
if rank will be 2, okay, if rank will be 2, that means this here will be your 0. Okay, let's take. That means only the first two vector will form your column space. Okay, I am talking about here column, not rows.
so the
Okay.
first
In
two
case of
vectors,
in case of rank 2, then the row space sorry what is row rank will also be 2 in that case.
Yeah. Yeah.
I mean it will be because uh,
Yeah.
basically
Yeah.
what it means is if column rank is 3, so column are linearly independent. That means we cannot generate one column from the use of other two columns. Basically, this is
Yeah.
what it means. But if the
Yes.
row rank, but if rows are not linearly independent, in that case we can generate the fourth row or any row by the use of other three rows, right?
Yes.
So, but my question is, this is rectangular matrix.
Hmm.
In rectangular matrix, it is not necessary that the column rank should be equal to row rank.
Why?
No, sorry, rank. So it is not necessary that the number of columns and number of rows are linearly independent because in square matrix, if
Yeah.
uh, in square
See.
matrix, if row are linearly independent, the columns are also linearly independent, and if
Yes.
rows are
Yes. Yes.
linearly dependent, then columns are also linearly
Yes. Yes.
dependent.
Yeah. Yes. In rectangular matrix, it is not necessary. Yeah. Okay. So
Thank you,
yet,
sir.
here rows will not be linearly independent, but columns will be linearly independent. Are you getting it?
But
Yes,
the
sir.
ranks will be same, right? For
Yeah. Rank will be same.
same,
Okay.
yes. Hmm.
Yeah, because the rank is 3. That means only 3 vectors in column will span the column space. Okay, so therefore only 3 columns. So all of these 3 will be needed. Okay, that means all of these 3 will be needed to span the column space, and that is the minimum number of that. So that will give you the linearly independent set. Okay, does anybody has any doubt in this option?
No, sir.
Sir, if sorry, sir, if on the first question, on
Yeah,
the first option, if A would be 4,
a
then
would a would be 4.
rank of A is 4.
That can't be. That can't be.
It is not possible, right?
Yeah, because it is a 4 cross 3 matrix.
Yes,
So
sir.
the maximum rank it can take is 3. Okay, it can't take rank 4.
Okay.
so I didn't get still the second option.
See, did you get why first option is incorrect?
Yeah, I got that. Yeah.
Yeah. Okay. So how are you saying that? Like why? third option. Why? First option will be incorrect. Okay, because we have three vectors in R4.
Right.
Oh, sorry, four vectors
Four
in
vectors in R3.
R3. One thing is this. The second thing is this, because there are only three non-zero row. Okay, after row reducing it, there are only three non-zero row. So out of the four vectors in row, okay, only three will span the row space. Okay, so that means only three will be linearly independent. So all four vectors in rows will not be linearly independent altogether. Okay,
Okay.
same as for column, because they are only the number of pivot element. There are number of columns in which we have pivot element. There are three. So that means all these three columns, okay, will span your column space.
There are three dependent variable and like we can say three independent vectors. Okay.
Okay, these
Now I
three.
got it. Okay.
Got it?
Mhm. Okay, got it.
Now,
Sir, in this question, we can also use one approach, that alpha, beta, gamma approach. If we go row wise, we will get the values of alpha, beta, gamma as non-zero, and in case of column, we will get it at zero.
how are you going to then decide the vectors? See, here I am taking one example to show this, but uh, see, this method will be great if you go by like row space and column space.
Okay. Got it.
Now, for third option, it is saying A is a non-zero matrix of order m cross m plus 1. Okay, that means the number of columns are one greater than by the number of rows. Then the maximum possible nullity of A is m. Is this correct?
It's m plus
No,
1,
sir.
Yes.
right?
No.
No.
Yes, sir. Yes, sir.
It will be
Yes.
correct. Yeah, yeah.
See,
It will be
by
M.
rank nullity theorem, we know that rank plus nullity is equal to number of columns,
Column.
right? If a maximum possible nullity, when will maximum nullity will occur? The rank will be minimum, right?
Yes.
Yeah. So if maximum nullity is m, then by rank nullity theorem, rank will comes out to be 1,
Yes, sir.
right? And
Minimum
that
rank would be
should
one.
be then, and that should be because A is your non-zero matrix. That means it should have minimum rank to be 1, right? If rank will be 0 for A matrix, then it will have 0 matrix. Correct?
Correct, sir.
Got it? Any doubt in this option? No? Okay.
Can you
Yes,
write it algebraically down?
this option is
Just write
correct.
the equation.
One by one, one by one. Yeah.
Just write the equation, whatever you just said.
Okay. I was just saying that the rank plus nullity is equal to number of columns, right?
Correct.
So it is saying that when nullity will be maximum, the rank has to be minimum,
Correct.
right? So if the maximum nullity is given as m,
Okay.
okay, and A is your here non-zero matrix, right?
Correct.
A is your non-zero matrix. So it should have minimum rank to be 1. Only then it can be a non-zero
Maximum
matrix,
nullity.
right?
Yeah.
Because if it will be like that, then its rank will comes out to be 0. A zero matrix has only rank 0,
Correct.
right? And because it is a non-zero matrix, so the minimum rank it can take m,
Correct.
sorry, 1. So 1 plus m, the number of columns is also
M plus 1. Yeah.
1 plus m, right? So these will comes out to be equal. So that's why this option will be correct. Got it?
Correct.
Hmm. Okay. Now fourth option. If A is your non-zero matrix for order 4 cross 5 and rank of A is 3. So if rank of A is 3, what will be the nullity of A?
2.
2.
2, right? By rank nullity theorem. Then the dimension of the solution space of homogeneous system X equal to 0 equal to 2, right? That x equal to 0, that means the null space would say, and its dimension will be nullity. So that
Yeah.
is 2. So it's
Correct.
correct.
It's correct.
Okay. Any doubt in this question?
No.
No? No. Very good. Yeah. This is your next question now. W be a proper subspace of inner product space V. Okay, so this is on the data, sorry. And the dimension of V is 3, and PW is the projection of V on W. Then this is your first question, that if V belongs to V as a norm phi, then what can be the maximum possible norm of the vector PWV? Yes, Alok, what's your doubt? This comes from the property of projection. Okay.
Like if we project, then the length will not change, right?
No, but this is not about that. Okay, I will discuss it. So, should we move toward solution, or are you guys following it?
Just 1 minute.
Okay.
Please go.
Okay. So, P is a vector, then the maximum possible norm of the vector PWV. Okay. There's one property of projection. Let's say this is your vector V. Okay. If you are going to project in on W, okay, then we know that this is your hypotenuse, this is your perpendicular, and this is your base. Okay. So the length of V, okay, the
V
norm of
square plus
V
P square.
will less than or equal to its projection. Okay, this
Correct.
is your PW. Okay. Oh, sorry, I will it on the side. No, sorry.
Greater than or equal to, no?
Yeah, sorry. That's what I am doing. Yeah. So it will be either greater than or it will be equal to. Okay. This comes with a property. Okay. So the answer, because it is asking for the maximum possible norm, so that means that can be what, which is when
5.
it can be equal to this. Okay. So it will be
Like
5.
5 cos
Correct.
theta.
So norm means what? The length.
Yeah, the
Sorry.
Length.
length.
Okay. Thanks.
Okay. So yeah, the projected vector image, the projected vector can have length equal to or less than. It can have its length greater than to it.
Now,
Okay.
suppose if the coordinates of this thing were given, then there's a formula, no, for projection W.
Yeah,
What
that's
is the
what.
formula?
Uh, it was like if you want to project V on to W,
W.
then PW of V will be like V comma
Inner product
W,
VU, VW, yeah.
where WI are like, if W1, W2 are the like basis of orthonormal basis of W. Okay.
And that is also divided by the norm of V, no?
Yeah, I am saying like the orthonormal basis.
Okay.
So already they are orthonormal. Okay.
If they are orthogonal, then divided by norm of
Yeah,
V.
normal. Okay. We may have one
Suppose
question.
if V is in W, then what will be the projection? It should only
What?
if V in W and we are
Yeah, then
projecting
its projection will be the same vector, right?
7, and then at that time only it should be 5 for this.
Yeah. Okay. So now this is also the follow-up question. Okay. Which of the following options are true? The data will be the same of the above question. Okay.
Sir, from which week is this stuff from, sir? If you don't mind telling me.
This is a quiz to paper. So it is from week to 8, and this question is from week 8.
Week 8. Okay, okay. So because okay, yeah. Thanks.
Yeah, so should we move to our solution or you guys need more time?
Yes, please.
Okay. Just 1 minute. Yes. So first option, I guess this is the only option which you guys might find a little bit hard to prove. Okay, all others are easy. So first option
It
is
will be like
if
easy, no?
V belongs to V, then V minus PW of V is orthogonal to W. Orthogonal means what? Their dot products will comes out to be 0, right? That means V, okay,
Both should be like 90 degree between the angle between both of them is 90 degree, right?
yeah, okay. PW, okay, V minus PW is orthogonal to W.
Any vector
Okay,
from W.
so let me write it. Let's say I am taking U belonging to W,
W.
okay, U, such that uh, W has some basis W1, okay, W1 till WK, and U is my its linear combination, right? CW1 till CWK, okay, C1, C2 or whatever. U is my like this. So any vector I can represent, right, from it. So V minus P W. Now let's say I am projecting it on V because U is our my uh, linear combination of W, okay, with U, okay, and this should be 0. Till now, did you guys got it or not? Is this clear till now?
No, can you explain it once
Yeah.
again, please?
Okay. See. Let's suppose U is my one vector from W. Okay. And W has some this basis, right? This is the basis of W. W1 till WK. Okay. And we know that we can represent any vector by some linear combination of its basis, right? So use my that vector. Okay. So V minus PU at W. Here I am projecting it because if when we are going to project, we are going to project it on like how our projection formula is, right? U dot V, oh, times U. Okay, where U will come out to be the like it will take every basis element, right? W1 till WK. Okay, so it will be like W1 times V divided by norm of W1 times W1, okay, till WK with V divided by norm of WK, okay. That's how it will take, okay. Got it now?
That will be middle pass
Hello.
by U also, right?
So V
No.
minus projection of
Yeah.
V W will represent vector which is perpendicular to W.
No. Yeah, what are you guys telling?
So projection of V, V minus projection of V in W, what will be it will give? It will give perpendicular vector to W.
Yeah, yeah, that's what this
This
basically
is the
means.
first step in this finding the orthogonal vectors, right? We usually
Yeah,
take the first vector
yeah,
as v1 and then second vector
yeah,
as
by Gramston process it will
yeah,
comes out, right?
yeah.
So
This is
I
also,
will
yeah,
say
if you know, say If you know the Gram-Schmidt process, then you can like directly tell, right? Because that's how you find your Gram-Schmidt process, right? Orthogonal vectors.
Yes.
So why we subtract it from its identity vector in its projection?
Uh, your voice is not clear. Can you please
Why
repeat?
we subtract it from its identity vector?
And that's yeah. See, you are asking why we subtract.
Yeah.
Yeah, because we are going to find the orthogonal. See, if you read the Gram-Schmidt process, that's what we do, right? We subtract its projection from the original vector, and that's how we find the orthogonal vectors,
So
right?
that is only that I cannot understand in lecture why you are subtracting from
Yeah.
it.
See, because then that's how we will go the like I'm going to prove it. See, till this step, did you understood?
Yes.
Okay. Now after that, from the property of inner product space, I can write this thing here. So this portion here, I can write it as inner product of uh, V with U, okay, minus inner product of uh, right. I can write it like that, okay, from the property of inner product space. Okay. Now this is remain as it is. Now here it's the projection thing, right? So if you do the projection, you will get this norm of U, okay, multiplied by, okay, so here it will come out to be norm square, okay, because when we do, so it will be norm square. So and here it will be U, okay. So U dot V minus this U dot V dot U. So U dot U will be basically what, your norm square. So this will cancel out. Oh, I forgot one U here.
Yeah.
The one U from the projection. Yeah. So
And
it will be,
how did norm square become? Yeah. How did the norm square
yeah.
come?
See, uh, like see PW, when you are going to project it, you will going to do either you can write it like this. That is like you take the your
Orthonormal.
orthonormal, right? And if you are going to take the orthogonal by normalizing it,
Then
okay,
we divided by
then
the
you are
norm of u.
okay. And because norm of you one will come from here and one will come from here, okay, so it will be like norm square, okay. See,
Oh,
because of
okay,
from the
okay,
inner one, okay,
okay, okay.
so it
Because
will be norm square.
that is also orthogonal. Yeah, yeah. Okay.
Yeah, okay. So it will be like inner product of UV minus inner product of VU, so that will comes out to be 0, okay. So that's why we subtract it to find the orthogonal W. Or in one line we can solve it like,
Sir,
because this is just,
can we go ahead with the diagram like V minus PW? It will be like the orthogonal vector, right? The projection
yeah,
vector. Yeah.
yeah, because this is what our Gram-Schmidt process do, right? We subtract the projection of that vector from the original vector, right, to get the orthogonal to the subspace W, right? So in one line we can say like it's from the Gram-Schmidt process, this will be orthogonal to W. Got
Okay.
it?
Got it. Got it. Yeah.
Hmm. Okay. So second option is, if dimension of W is 2, then the dimension of null space of PW may not be 1. Okay. We know that the projection of vector follow a linear transformation, right? The projection of vector follow a linear transformation. Okay. Where what will be the its image? Can anybody tell me what will be the image of this linear transformation?
Projection.
Yeah, it will be the projecting vector, right? And that means what? It will be in W, right?
Correct.
Right, and W has dimension what? 2.
2.
2. And above it is already given that the dimension of V is
3.
3.
Yeah.
3. That means by rank nullity theorem, we can say that the nullity will be 1, right? By rank nullity theorem, we can say that the nullity will be 1,
Correct.
correct? And nullity represent what? The dimension of null space,
Correct.
right? And here null space is nothing but the orthogonal complement, right? Okay, so the orthogonal complement of it, that means the null space of PW will have dimension 1, but here it is saying it will not be, so this will be incorrect.
So, I mean, what does it, the complement means here? The PW
uh, that
projection
means
of
the vectors will be orthogonal. Okay, the vector in that set will be orthogonal to W. Okay,
Can you please explain once more, sir?
yeah, see, we know that our projection follow a linear transformation, right? That okay, and its image is projecting vector, right? PWV, okay, which will be in W, and W has given dimension 2. Okay, W has dimension 2 that is given already, and the dimension of V is 3, right? The dimension of V is 3, but from 3 minus 2 it will be 1, and it will 1 will be what? Nullity, right? And nullity represent what? The dimension of null space, correct?
Yeah, where it is given V is 3. Sorry.
It is already given in the above. Yeah,
Oh,
dimension of
okay,
V is
okay. Yeah, sorry. Yeah.
okay. Now the third option is very easy. Zero vector is orthogonal to every vector, right?
True.
True, right? This is
correct.
easy. If V belongs to W, then projection of V will be V, right?
Yeah.
This also comes from property
Correct.
of projection. Okay. So any doubt in this question?
No.
Okay, right. Now,
Hello, sir.
yeah.
Can I ask a question from activities?
Uh, After this question paper, okay? After we solve this question paper, then you can ask.
Okay, sir.
Hmm. So this is your next question. Here, you have given the definition of an inner product. This is like this, that any inner product in R2, you will do like that. Then you have to find norm of uh, 1 comma 3 square. Okay, norm square of 1 comma 3. This is a numerical type question. Just be careful that this is the definition of inner product here. Okay.
So 13.
Yeah, 13 is the correct answer. So should we? Does everybody solve it?
One more minute, sir.
Okay, okay.
Done, sir.
Great. Yeah. So we have to find the square of norm of 1 comma 3. Because any definition of norm is not given, then we will consider the standard norm definition, that is the square root of hmm, norm of 1 comma 3 square, that is inner product of 1 comma 3. Okay, so inner product of 1 comma 3 or will be with itself, right? So if you do here, it will be 1 minus 3 plus 3 plus 2 times
0 plus 2 times 9.
9, 1 minus 6 plus 18, so it will be 13. Okay, any doubt in this question? No. Okay, now which of the following are unit vectors?
So norm of
This
the
is
is under root of inner product. Na?
what?
Norm of any vector will be under root of inner product defined
Yeah,
under.
but here it is norm square, right? Here it is norm square, so that will be just the inner product.
Just scroll above one.
Hmm.
You have
Here
written that.
it is the norm square,
Okay, so you have
right?
put that
So that,
in under root.
yeah, that will be just the inner product.
No,
Okay,
no, you have written under root norm of 1 3
yeah,
comma
so because we have yeah, because see, I have written like that because the norm of 1 comma 3, okay, it will be like the under root of its inner product, right? And it's the square, so it will be just the inner product. Okay,
So it will be again under root na, because the root is not used.
okay, just remove. Okay, it will be same. Okay, yeah. So which of the following are unit vectors here? See, the definition of the inner product is same as defined above. Okay, in this question also, we are taking the same definition of inner product that we are defined above.
So can you show that, like, the definition one?
Uh, okay, I will write it here.
Okay.
This will be x1 x2 minus x1 y2. Okay, this was your definition. Perfect. It was 2x 2y. Two y1 y2. Not x. So should we move towards solution part?
Yes, please.
Yeah. Okay. So for 1 comma 1, what will be the inner product of 1 comma with 1 comma 1?
1 only.
Okay. So that will be 1, right? Inner product of 1 comma 2 with 1 comma 2.
It will be again 1.
Okay, if you see the 1 comma 1 by 2 of 2 comma 2 is nothing, just the 1 comma 1, right? So it
Yes.
will be like same, or else you can try.
1 by 2 comes out, which becomes 4. 1 by 4.
Yeah, it will comes out as 1 by 4,
Correct.
right? Because 1 by 2 from here and 1 by 2 from here.
Yeah. So inside it will become
And
4. 4 by 4 is 1.
yeah, correct. Okay, so it will be 1 by 4 times 4, so that is again 1. For 1 by root 13 of 2 by 3, it will comes out as 1 by 13, and then it will be like it will be 9. So yeah, it will not be 10.
Correct.
Minus 8 plus 18 for 10. So it will not be 1. For 0 comma 1, if you check,
This will become 2.
0 plus 2 times 1, so it will be 2. Okay, so these are wrong, these are the correct. Okay, any doubt in this question?
Any
No.
reason why we are taking out that 1 by 2 or 1 by root 13 out?
uh, you can directly do it, but see, we can take out, you can do anything. Okay, if you want, then you can calculate your expression by taking them as inside, or if you want, then you can take them out. Okay, it's up to you, you will get the
Okay.
same answer.
Okay, so if we take them out and we have to multiply.
Yeah, because see, here there are two scalar, so they will come out by 2 times, 1 by root 13 times 1 by root 13, so it will be 1 by 13 here. Okay.
Okay.
Now note this information here. Okay, what is the definition of T and definition of S and your ordered basis beta and gamma. Okay, after that we will move on to the question. First note these details here. Yeah, and then this is your question. Okay, it says the matrix representation of SOT with respect to order basis beta for both domain and codomain, then order of A m cross n, then find the value of m plus n. I'm sending the link of feedback form. Please fill this. Okay. Yeah, so should we move towards solution part?
Yes.
Okay. So T is your this and S is your this and this is S of T. That is the composite function, right? This. So f of T of x comma y comma z. Here it will take the image of T of x comma y comma z, which is this here, right? So f of x plus y comma y plus z. Okay, and what this will be? This will be this here. It will be x plus y comma y plus z comma x plus 2y plus z. Okay, so basically our f of t of x comma y comma z will be your x plus y comma y plus z comma x plus 2y plus z. This is your f of t. Okay, till now any problem?
So can we explain
No.
again to the composition function how to take the domain and domain?
Okay, see, f of t is what? F of t of x comma y comma z. That means here it will take input from t, okay, and then what will be the output of t here? X plus y comma y plus z, okay, and that will take as the input for this s, okay, x plus y comma y plus z. And what will be the image of s? X comma y comma x plus y. So here this is your x and this is your y. So x comma y comma x plus y, right? So that will come out as here. Okay. Then this will be your linear transformation then. Okay.
Yeah.
Got it? Now this is for order basis beta, and beta is your standard order basis of R3. Now you just have to find the matrix for that. So f of t of 1 comma 0 comma 0 1 comma 0 comma 1, right? F of t of 0 1 0. Okay, f of t of 0 comma 0 comma 1, it will be 0 comma 1 comma 1. Okay, what is basically asking the question? Oh, it is
So
just only asking
this
about the
x
f.
plus 2y, right? Like 1
Hmm?
comma 1 comma 2 it will be. 1 3 1 plus. Okay, x is 0. Sorry.
In the question, it is just basically asking for the m plus n. Where m and n are the order of the matrix. So yeah, what will be the order of the matrix here? Hmm?
3. I got 3
6 of
cross
3, right?
3. Yeah,
Right. So m plus n will be what? 6.
6.
Yeah. So that will be
Can
your
we write
answer.
down the matrix A also?
Uh, Matrix A, then it will be 101, 112, and 011.
Or,
Okay.
or this is a standard order basis.
Yeah, this one was standard order basis, right? So you can just directly put the vectors in column. Okay.
For this question, do we really need to make a matrix, or we can identify
No, no.
with the
You,
R it is given, right? The transformation R3 to R2, that means the very first.
transformation was from R3 to R3 for SOT. For f of
Yeah.
t,
So
the
can't we find
transformation
out
will,
with the information
yeah,
which is given with R3 to R2 and then S is given
uh,
what? R2 to R3, right?
yeah, yeah. You don't even need to find the matrix.
Yeah.
for you.
Okay.
Yeah.
Can you show it once, that method? Just I want to confirm.
See, it was from R3 to R2 and then R2 to R3. So S of t will be from R3 to R3. Okay, so it will be
Yes,
3
yes,
source
correct.
symmetry.
Yeah. Mhm.
So the gamma had no role in this entire
Uh,
solution.
Still the questions are left. See, there are sub
Acha,
questions of
acha,
this.
acha. Okay.
The question is not yet complete. Hmm. Now, if K represent your null space of S of t, then find the value of A by B minus 2 times C by D, where A, B, C, D are these values. Okay.
So the K is another transformation, what?
Now, K is the null space of this transformation S of t. Okay.
Oh, it's a null space. Is it?
So can we show the equation once? SOT. So okay.
Sir, I also want to see once.
This is your SOT. Okay.
Okay, sir.
Haven't you all found this S of t? You should found this by yourself. Yeah, so should we move to our solution part?
Wait, sir. Wait.
You guys need more time. Okay. Yes, Kirti, what's your doubt?
Sir, in no, previous two questions,
Uh, in the previous question,
no, sir. Unit vector of V. So unit vector means it should be 1. It should be equal to 1.
the norm of that, the length of the vector.
Length of the vector.
Okay.
Okay. Should be equal to 1.
Yes.
Okay.
Okay, so now should we solve this question?
Yes, please.
Hmm. So this was your f of t, right? F of t was this, and to find the null space, what we can do, we can equate it to 0 comma 0 comma 0. From here we got these equations. So if you're going to form the matrix of this, you will get this. Okay, now we just have to row reduce this matrix. Okay, after that you can do r3 minus r2, 0 1 and 0 0 0. So basically you got y plus z is equal to 0, x plus y is equal to 0. Okay, and how the null space is defined? Ax plus by equal to 0. That means what? A times x plus b times y is equal to 0 and x plus y is equal to 0. From here you can conclude that A is your 1, B is your 1. Same, you will get C as 1 and D is 1. So in question it is asked for this, so it will be 1 minus 2 times 1, so minus 1. Okay, any doubt in this question?
Yes, I
Yes,
have. I did like this only, like, but I didn't make the matrix. I used the equation and I got
yeah,
-1. But my question is like, now we have a we have make our matrix A with the standard order basis, right?
yes,
So why can't we use that matrix?
you can use that. See, that will be the same matrix as here.
So we can
Okay,
use that also right now
yeah,
because the standard order.
yeah,
Hmm.
because see that this is the matrix A and this is the matrix. Okay, it will be the
Okay.
same. Okay.
All right. Yeah.
So its answer will be -1. Now, what will be the rank of f of t? We have already found out the null space.
Can I ask one question, please?
Yeah,
The previous question, section 2,
if
yeah, this one. If K is
hmm,
equals to this one, right?
k is your null space. Yeah.
So
Hmm.
to find out a null space, you basically use the matrix which we got in the previous session, right?
Uh, yeah, because that was for standard order basis, right? So we can use that matrix. Okay.
Okay.
So just equate it to 0. Okay, you will get these three equations. After we will then form this matrix of these equations and row reduce it, and then this will be our null space. Okay, so what is the like, yeah, so what is the rank of s of t here?
Rank is 1.
Why, see, your s of t is from r3 to r3. What will be the dimension of null space? See, we already found out the null space, so what is the dimension of this space here?
Is it 2?
And the rank is 2. Okay, the rank of s of t is
Yeah,
2
rank is 2.
because
Null
the
space
null
is
space has same
1.
dimension.
Yeah.
Yeah, the dimension of null space is 1. The rank will be a 2. Okay.
Can you scroll up to the uh, row echelon form that you derived?
Yeah.
So
Okay.
here From this also you can say the rank is 2, right?
Yeah. From here also you can say.
What is ordered basis?
Hmm?
Ordered basis.
The order basis means you have to use your basis element in like this. Okay, you can't
Zero,
use. Hmm.
zero and one. It is the basis is in zero and one form. It is ordered basis. Is it?
No. See, that means like if you are going to form see, if you have given like some information like this. Okay, let's say this information is given. Okay, and if they are saying that your order basis is this. Okay, this is your order basis. So when you are going to form the matrix, okay, and the matrix and the here, when you are going to form the matrix you will got will be
One
this.
zero 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 one.
This matrix you will get. Okay, when you are going to form the matrix, if your order basis is this, that means first should be this, second should be this, and then third should be this. Okay, you have to follow the order in which they are written here. Okay, that what does basically order basis mean.
I didn't understood this.
Okay,
The transformation is given like this. So what is the which order? I did not
okay,
follow that.
let's say the order basis are like this. Okay, the standard order basis. And okay, let's take this example. Okay, s of t of x comma y comma z as so f of t of 1 comma 0 what this. Okay, now when we are going to form and you are taking like order basis for codomain also. So if you are going to form the matrix of this, then you will get this. Okay, but if your order basis for domain, let's say, are like this. Okay, mm. If your order basis for codomain, let's say this. Okay, see the difference here. Okay, if your order basis are like this, then okay, so your matrix then will be this. Okay, understood? See the difference here.
Yeah.
Whichever basis will come first in order, that will go in the order of the matrix. Okay, that's why we use ordered basis.
Understood. Yeah, this part I understood. This order basis, how will get it from basis? How will get it the order basis? Will be zero
No,
and
that
one
will
in
be given to you. No, that will be given to you. Okay, order basis that will be given to you. Now this is your next question. That a linear transformation is from R3 to R2, whose matrix representation is this. You have given the order basis beta and gamma. Then the nullity of the matrix A is Yeah, so should we move to our solution?
Yes.
Yeah. Okay. So this is just you have to do the row reduce form of this. What you can do, R2 by 2. So how many? So what is the nullity will come out to be here?
With not 0.
Nullity will not be 0. Nullity will be
Nullity will
1.
be 1 because rank is 2.
Yeah. See, the rank is 2. Okay. So the nullity will be 1. Okay. Or also you can see there are two pivots column here. Okay. So the nullity will be 1. Which of the following options are true? This is also from the same T. T was from your R3 to R2, whose nullity we have already found is 1. So, which of the following option will be true?
Will be over 2.
Okay, yeah, correct. Okay, because if nullity is 1, the rank will be 2, right? Which is same as the dimension of codomain. Okay, any doubt in this question?
Yeah, if you can explain the, because I'm still very confused about 1 on 1 and 1 2 and algebra.
If you have doubt in the concept, see, then you can ask in revision session. Okay, because if I'm going to explain the concept now, then it will take a lot more time.
I appreciate
Yeah,
it.
or I can do like after question paper. Okay,
No problem.
after that.
No problem. No problem.
Okay, yeah. If this is your transformation, then find the value of m plus n plus s minus 3 times p plus q plus r. Okay, the matrix, what was the matrix? Okay, this, yeah, 1 minus 1 0 0 2 3. Okay, and your basis for domain was 1 0 0 0 1 0 and 1 comma 1 comma 1. Codomain basis was 1 0 and 1 1. Okay, so then you have to find your t. And then you can easily find the value of this.
Codomain is gamma, right?
Yes, codomain is gamma. Yeah, so should we move towards solution? Hello, am I audible? So now, yeah, okay. So t of 1 comma 0 comma 0, we can write it as 1 times of 1 comma 0 plus 0 times of 1 comma 1, then we will get 1 comma 0. Okay, because that's how we find the transformation from matrix, right? Hmm. Plus it will be 2 times of 1 comma 1 2 and that will give you 3 comma
3
3.
commas.
Okay. Now I can represent this set. Oh, I can represent 0 comma 0 comma 1 as 1 comma 1 comma 1 minus 1 comma 0 comma 0 minus 0 comma 1 comma 0, right? Correct. If I take p both sides, p of 1 comma 1, substitute the value of t. Okay, so t of 1 comma 1 we already found 3 comma 3. This one was 1 comma 2 and this one was 1 comma 0. So you will get them 1 comma 1. Okay, so you have now t of 1 0 0 as 1 comma 0. So you can now easily define your linear transformation as y plus z comma 2y plus z. And if you compare it with the value of m and s and pqr here, you will get m equal to n equal to s to be 1, q to be 2, and r to be 1. And what 1 to n? P. Okay, and p to be 0. Any doubt till now?
So, how did you, can you scroll?
Hmm?
How did you find T001? I didn't get this.
Okay, I can represent 0 comma 0 comma 1 with this combination, right? 1 comma 1 comma 1 minus 1 comma 0 comma 0 minus 0 comma 1 comma 0, right?
Right.
Yeah, and just then I have taken t both sides, and then instead of t11 I substitute its value. Okay, that is
So
3
why
comma
we
3.
need to find out this 001?
Yes, we
Because
can
then we
do
will have the
directly, Can't we do,
FA.
no, can't we skip this step and do directly the below part? Yeah, like the XYZ part. We can do this directly, right? Transformation of this is we have got this. We can do it directly, right? And then we can take the XY X comma, I mean, what? X of 100 plus Y of 010 plus Z of that is equal to like one by one we can take out. Can't we do like that?
So see, you are telling
Yes, sir, we
you
can
have
do like that.
initially see, just wait. Initially you have given this. It was what 1 comma 2, right? And t of 1 comma 1 as 3 comma 3. So now you are basically doing x of 1 comma 0 comma 0 plus y of 0 1 0 plus z of this, right? And for this, if you are going to take, then you will get t of x plus z. comma y plus z comma z. Okay, if you are going to do it like this, then you will get you will not get t of x comma y comma z, you will get this. Okay,
And what is this then?
here it is t of x comma y comma z. Okay, see, if you are going to directly take this, okay, 1 0 0 0 1 0 and 1 1 1, then you will get the value of t of x plus z comma y plus z comma z, not t of x comma y comma z. Okay,
What we
that's
will
why we are
get from
converting it.
here, like, can we proceed this ahead, like
Okay,
suppose we have to
then
find x plus z, y plus z, and z.
if you want, if you are going to proceed, then you will get your transformation 3z comma 2y plus 3z. Okay,
Now
then this will be
my
your transformation here.
like now I can consider x plus z is equal to x and y plus z, like capital X, y plus z equal to capital Y, and z is like.
Uh, then that will be a different transformation. See, okay, that will be a different thing here. Okay, you can't consider that here. You should have t of x comma y comma z. Okay, only that. You can't like get the capital X and capital Y. No. Okay, only that term here x comma y comma z should here. So see, there are like two steps, two things. Either you convert your given basis to standard order basis. Okay, like just how I did. Okay, and then find the value of like what is the value of t 1 0 1 1 1 0 0 0 1 0 and 0 0 1. Okay, or you can, the second method you can try is this. Now find out the value of alpha, beta, and gamma, and then take your t both side and that solve. Okay, but yeah, if you are going to do it from directly here, then you will get the wrong answer. Okay,
Can we do this with this method?
the, the below here, the alpha, beta, gamma.
Yes.
Okay, so you will get alpha plus gamma is equal to x, gamma is equal to z. Put value of it here. So alpha will be x minus z, beta will be y minus z. Now substitute the value of alpha, beta, gamma here. X minus z of 1 0 plus z of 1 comma. Now take t both side. Okay. If you are going to take the t of 1 0 0 is what? 1 comma 0. X minus z of 1 comma 0 plus y minus z of 1 comma 2 plus z of 3 comma 3, and see x minus z, okay, plus y minus z plus 3z, okay, comma 2 times of y minus z plus 3z. If you are going to solve it, you will get x plus y plus z, comma 2y plus z, right?
Okay.
Which is same as that I got, right? Here.
Sir, we
Here, if
can
you,
also represent those inside x plus z as x and the transformation in terms of those, and then we can do, right? Like
uh,
x plus z equal to x, y plus z equal to y, and z equal to z, and represent the other two in terms of those. Then we can
That's what I said. What he
like
said.
it will be like same. Like calculated, it will be
uh,
same.
where? So you are telling
I
that
think
you are representing, yeah. Okay, so tell me. Oh,
The first term will be like what you got in the end, like x plus y plus z, and the second term will be 2y plus z, if you write it in terms of that.
so you are representing whole x plus y. Okay, let's take different thing. Okay, no.
we get same thing. I think. Yeah.
if you are doing both side, are you doing both side?
Yeah,
Yeah, we have to do both
Yeah,
side,
yeah.
no? Okay.
Yeah, if you are
because
doing both side, yeah, then you will get same. If you are
yeah,
doing
because
both
the
side, then
matrix
you
is
will get.
given, because the
Yeah,
matrix is given, we can directly get the
yeah,
transformation, right?
yeah. See,
So
Yeah.
if you are doing both side, then you will get. I thought you are just doing from one side. Okay. Yeah. Okay.
Okay,
If you are
now
doing,
can you tell me the first method, what you
yeah,
said,
first
guys?
method is just like if convert all of them to standard order basis. Okay, find the value of t of 100, 0, 1, 0 and 0, 0, 1.
Yeah, that
Okay.
is okay, but after that you have subtracted it, I think. Where it is?
Oh, that because we have given the value of
Yeah,
t
this
equal to 1.
one. Yeah.
So I subtracted to find the value of t of 0, 0, 1.
Okay, okay.
Okay. Then we have the value of standard order basis of t, and then we will got this transformation. Okay.
Okay.
You were talking about a method, Miss Tarika. Can you yeah.
Hmm?
Hello?
Yes. Any doubt here? Okay.
Sir, can I ask my question now?
Uh, do you have anything related to this question?
It's related to affine transformation.
Fine. See, we can discuss that after the question paper. Okay. Uh, only like I guess few more questions are left. Okay. After that, uh, yeah, this will be our like last question, and we have like only 2 or 3 questions from this data set. Okay. Note down these points here which are given. Okay. That L is equal to U and L dash is this. And yeah, see, this question is also from a fine subspace. Okay. So if you have doubt, then you can clear that here. Okay. Use span of this.
That this question is from
Give
the
this.
reflectivitas question.
Yeah, the same question. Okay. Transformation is this, and again these things are given. F is your affine mapping, like this. Okay. Note down these data points.
Like this question took us 1.5 hours to like solve.
This
So
is now we can solve it in 10 minutes.
yeah.
Okay, so did you note down these data points? Yes or no? Hello? Okay.
sir, proceed.
Yeah. First is asking about the find space of L.
So the answer is already like you did it in the reflect. Maybe you can proceed with the answer. Right.
Yeah, if all of you are okay with that. Nobody is saying anything, then yeah, we can proceed. Okay. So here L is your what? U, and U is your span of these three vectors. If you see, there are three vectors in R3, right? And three vectors in R3 will form a basis, okay, of R3. So U is basically or nothing but R3, okay, and L is equal to U, so L will be also your R3, okay. Any doubt in this question? No.
So can you say it again? Sorry.
Why did we cancel the first two cost thing?
See, L is your what? U, and U is
Correct.
nothing, and U is nothing but the span of these three vectors.
Correct.
There are three vectors in R3, and span of that means it will form the basis of R3, right?
Correct.
So U is nothing your R3. So L equal to U, so L will also what? R3.
Okay.
Okay. Okay. So L is R3.
So we have to confirm that the span is the basis before answering, or
See, span of three vectors in R3 will be what? R3, right? Span of three vectors in R3 will be your
will always
R3, right?
okay.
Okay. So that's why L will be your R3.
It doesn't need to be basis, right?
Uh,
Yeah,
but three
that's what I
vector,
was thinking.
It
yeah,
should
you
be
can take
only three
you can take
vectors.
they are linearly independent here. These three you can take they are linearly independent.
Okay. Okay.
Okay, so span of these three will be your R3
Why did we nullify the first three options? Just
because
because we got the right answer, is that?
yeah, of course these three will be correct because incorrect because it's a multiple choice question. So these three will be incorrect if this one is your correct. Okay, and besides that the other three, if you check, they have dimension 2 while L has dimension 3. Okay, so they obviously can't be your answer. Okay, so now next question is about L dash.
So you said something like dimension is 2. Can you repeat?
Yeah, I was telling like the above three
Yeah, yeah.
option has dimension 2, okay, while your L has dimension 3, so obviously they can't be your answer, right?
That's why.
Now what is L dash? Where it is? L
Elder
dash
is
is,
dimension 2, right?
yeah, L dash is 2 comma 0 comma 1 plus U dash, and U dash is the span of these two vectors 101 and 011. So U dash, and U dash is your span of, so that means,
So how this is
This is L
done?
dash. Huh?
yeah, sorry, not L, this is L dash. Okay, so your U dash is basically comma x plus y. That means U dash is set of all x comma y comma z. Okay, such that x over all set of x comma y comma z such that z is equal to x plus y, right? Correct. That means x plus y minus z is equal to 0. That's how your U dash is defined. Okay, so L dash is equal to nothing but 2 comma 0 comma 1 plus u dash. So that means 2 comma 0 comma 1 plus zero. So if you are going to add, you will get x plus 2 comma y comma z plus 1, and this will be like that. What? X plus y minus z equal to 0. So that means x plus 2 plus y minus z minus 1 should be equal to 0, plus y should be equal to minus 1. X plus y minus z is equal to minus 1. Okay. Oh, did we do some mistake?
Answer 2. Option 2.
Uh, no, but we are getting minus 1. What happened?
No,
I think we have to represent that each x, y, and z with like x is equal to x plus 2. Like capital X is equal to x plus 2, and like that we have to do it.
Yeah,
Yeah.
that's right.
Okay. Let's go by then one by one we do. Okay. So that will be your x plus 2 comma y comma z plus 1. We are going to represent it like that. Then z is equal to x plus y. Yeah, it means plus 2 plus y. From here, x plus y minus z is equal to 1. Okay.
Right.
Okay. So this will be your correct answer. Now, which of the following represent f correctly? Try to solve it. Yeah, so should we move to our solution? Okay. So 201 and 110, and this one is 1. Your mapping was defined. Okay. So f is your mapping from 2 comma 0 1 plus t of u, where your t of x comma y comma z, okay, you are given these values. What it was? 110 101. Okay, and 0 1 0 belongs to kernel, that means it is 0 comma 0. Okay, for now
It's just given the last one transformation is given. It's like belongs to kernel.
these values are given. Okay, these values are given to you.
Okay.
Okay, now there are like two ways. One, either you convert it to standard basis and then find, or you want me to directly find. Which way you want me to find?
Like
Then order.
we directly can write it down in the linear combination of the codomain, right?
Codomain? But see, you have to see what will be the domain here. Okay, so do you want me to find like how you found, like, then?
The domain
Okay,
is U, right? Right.
yeah, but first let's find the transformation I am talking about. First let's find the transformation. What will be the transformation I am asking? How are you going to find the transformation?
Can we go via standard order basis?
uh, yeah, you can go, but then you have to convert. That will be a very lengthy process, because then you have to convert, uh, like, you have to find what linear combination will this represent, 1 0 1 0 0, and then all. Okay, either way you can find it like this, or let's just found me directly. Okay, because this part we already know. Okay, so it will be, wait. Yeah, this will be like that. Mm. This you can try to find it by yourself if you are not getting. Okay, this will be the transformation that you will get. Okay, or do you want me to explain it fully, how I got the transformation?
Yeah, better if you can.
uh, Fully explain. Okay,
Yes.
so no, and consider it this equal to, hmm, this one was 2x plus y. Okay, here if you want convert a, how will you got y here? You can get y here by 2x plus y minus 2 times x, right? Which is nothing but alpha minus 2 gamma, right? Okay, similarly b is your x, that is nothing but gamma. C, you can get c by, c is your x plus y. Okay, which you can get by 2x
Gamma by
plus
two.
y, which is alpha minus gamma. Okay, that means t of alpha beta gamma here is nothing but alpha minus 2 gamma gamma alpha minus gamma. That is K of x minus z minus 2z comma z x minus z. Okay, got it now? Hello, is this okay?
Yeah.
Yeah. Okay, so now your mapping was 201 plus t of u. Okay, so you just need to add 2 comma 0 comma 1 plus t of x comma y comma z x minus 2 f of u here will be x minus 2z plus 2 z as it is x minus z plus 1. So which option is this? This one. Okay, so this will be your correct answer. Yeah, so any doubt in this question paper?
Yeah. Can you please explain that projection question
Yeah,
again?
that orthogonal projection part.
And somebody said that it's Graham Smith. I couldn't correlate actually with the Graham Smith.
Okay, this one, right?
Yes.
The first option. Okay, so okay, 1 minute. Hmm. Yeah, are you able to see my screen? Hello.
Yes. Yes.
Yeah, so yeah, sorry. Hmm.
Can you zoom? It's
That's what
too
I'm doing.
tiny. Yeah.
Hmm. Okay, now it's clear. Are you able to see?
Yes.
Hmm. Okay, see basically what is happening in step 2 here. If you directly see what we are doing, why uh, we are taking one vector, okay, and we are subtracting it, the inner product with multiplication of the vector. Okay, let me read what are the things here. A slight modification yields. Okay, we are given a vector, we have given a basis set. Okay, how are we find the orthogonal basis from this basis set? By Gram-Schmidt process. What we do, if we want to find v2, okay, let's say we want to find one vector which is orthogonal to v1 here. Okay, for finding it, that what we do, v2 minus inner product of v2 with u1 multiplied with u1, and u1 is what, the normalized form of v1, right?
Are
Correct.
there different ways of writing these steps? Because what I have written with me is
Yeah.
W2,
These are
WT.
just notations. Okay, so these are just notations. Okay, you can
In
just work them.
lectures, sir use some other
Yeah,
notation and like
But
these are
that.
just notations.
yeah, but still V2 is the vector which we have created already, right?
No,
Like,
v2 is the from basis. See, v2 is from basis.
oh, here it is from the basis. Oh, I
It
was
is basis
thinking
and
like
Yeah,
what we have make it. Okay.
so that's what basically here it was. in this, right? V
Okay.
minus the projection, right? Here also it was what? Projection thing, right? So that will give you what? Orthogonal basis, right? The
Oh,
orthogonal
this is
vector.
related to projection. Can you?
This is the projection, right? Here you are projecting your u1 on v2, right? See the projection thing here. That's how we project, right?
Yeah, yeah. That's how we
V
project.
comma vi, inner product of v comma vi times vi, right? So here also the same thing. v2 minus the vector, the projection of the vector on v2, right? Same thing is happening here. V minus projection of v on w, right? So that will be your orthogonal, okay, to w, because here
But
it is
that W is on the same basis, right? Some same space, like in that V.
v is belonging to w. Oh, v belongs to
V.
v here, okay.
But here in that slide that we showed,
Hmm.
it, here the U2 belongs to same, right? Same basis, right? So that should be
The
from same
u2,
space, now.
u2 is different. See, the vector you are get, uh, okay, the vector you will get after that, that will be orthogonal, okay. That's the main key point here, that the vector you will get here will be orthogonal to each other, okay. Whether it is from v or w, the vector that you will get after this process will be your orthogonal vectors, okay.
That will be orthogonal. The U1 that will be orthogonal to V, right? That basis.
The v, okay, the w2 that you will get here will be orthogonal to w1, okay. Is that
And
okay?
also W is orthogonal to V, like gamma, that basis.
No, it is not orthogonal to each basis element here. It is here only orthogonal to w1.
That space of that basis, no?
No, it is only orthogonal to w1 here, because till now it will be orthogonal to w1. Okay. If we go by whole process, then every vector we will got will be orthogonal to each other. Okay. Are you getting it? Hello.
Is it possible for you to cover the properties from week 8?
Which
Can we
property?
check?
Like all the properties related to projection and rotation matrix.
Projection. Okay. Projection. Okay. Uh,
When
I
can we
also
take that onto and one stuff?
okay. Okay, for projection, I also have to see what are the properties given. Okay, like one property was like this. Okay, and one was, I guess, pw square is same as pw, right?
Excuse
And
me, sir.
Yes.
yeah, yeah. Okay, so these are
Please.
the properties already given in the lecture,
Yeah, sir.
right?
Like yesterday, we also told that you that we didn't
Yeah.
get the part. So
Oh, the rotation matrix.
rotation matrix, the orthogonal matrix, some property of that.
Okay.
Like summary of weekend. Can you explain conceptually?
Okay, I will explain that. Yeah, before that, like somebody was asking from week 7, right? 7.2 question number.
Activity 7.2, question number 8.
I will explain that orthogonal matrix. Okay, just give me a minute. Yeah, this question.
Yes, sir.
Okay,
Uh,
just a minute. Hmm. Okay, see here. Here you have to do both. You have to consider an affine mapping. Okay, an affine mapping no, will be in the form of this. Okay, okay. Now you have given here f of 2 comma 3. Okay, that will be 2a1 plus 3b1 plus c1 comma 2a2 3b2 plus c2. Okay, which is equal to 3 comma minus 1. Okay, now f of 2 comma 1 is given here. It is also given as 1 comma 2. Okay, and same f of 1 0 is given as 0 comma 1. Okay, now if you see, you will get some equations here.
So by solving equations and getting the values, we have to find them.
Yeah, then you will find the a1 b1 c1 a2 b2 c2, and whatever you will get value. Here you have asked for f of minus 2 comma 5. Put x equal to minus 2 and y equal to minus 5. Okay, and the values you got for a1 b1 c1 a2 b2 c2, and then that will be your answer. Okay,
Okay, sir.
got it?
Thank you.
Hmm. Yeah, and somebody has brought in 1 1 and on 2, right?
Yeah, 1 1 and on to that. That is the case.
Okay, if t is your transformation from v to w. Okay, for 1 1 and on 2, first three thing you should check is dimension of v and w. Okay, let's say dimension of v is n and dimension of w is m. If m is greater than n, that means the dimension of codomain is greater than the dimension of domain. Okay, then it can never be onto. Can never be onto. If dimension of domain is greater, then it can never be 1 1. And if both has same dimension, then either it will be both or none. Okay,
How does this pictorial
and
diagram looks like? Like onto means like domain has got one element which will have images, uh, two images in W. Okay. Is that something which is called onto? And if the image from the domain to codomain is just I mean one each, so it would be one and one.
no, this is what for 1 1, but what basically means is every vector, okay, here in V should only map to one vector in the DOM.
That is one,
Okay,
right?
yeah, if this case happened here, right, like two different vector in V got mapped to same vector in W, then
But
it will not be 1 1.
it can be onto.
Okay, the onto condition is that the range of the function, okay, would be equal to codomain.
Sorry, come
Okay,
again.
if range is equal to codomain, then it will be 1 on 2. Okay, if range is equal to codomain, then it will be on 2. Got it?
How can you present it? Is there any example maybe with two elements and R2 we can show?
Let me do this.
Okay, while searching, may I ask one question? This week 5, tutorial 1, 2, 3, they seems to be having mention of week 7. Is that correct?
Hmm?
Tutorials are there.
Tutorial.
Yeah,
Yeah, 1 to 3.
yeah. Click anyone. It shows from week 7.
Uh, yeah, it shows it's just the title, okay. But yeah, content here is from week 5. Okay, it's just the title. Let's say this is your T. Okay. Now, as you can see, the dimension of codomain and domain are equal. So either it will be both 1 1 and onto or none.
Okay.
Okay. For 1 1 condition, if T of x comma y is equal to 0 comma 0, such that you are getting it only when x equal to 0 and y equal to 0, then it will be 1 1.
Okay.
So for that, you'll get here these two equations, right?
Okay.
Okay. From here, you will get x equal to 0 and y equal to 0.
Okay.
Okay. So that means this condition is satisfying. So it will be 1 1. And because both have same dimension, if it 1 1, then it will be onto 2. Okay. Or the other method you can try is you can form the matrix of this transformation. Okay. You can form the matrix, find its rank and nullity. If nullity comes out to be 0, then it will be 1 1. If rank comes out to be equal to dimension of W, that means codomain, then it will be on 2.
On. Nullity
Okay.
is 0 when it is 1, 1. And the
Hmm.
rank is
If
dimension.
rank of W,
Hmm.
okay, then it will be 1. Got it? No?
In square matrix, perhaps mostly there'll be 1, 1 and on 2, right?
No, either it will be both or none. It means if it is 1 1, then it will be on to 2. If
Yeah.
it is not anyone, and then the other one will automatically fail. Okay.
Correct, correct, correct.
So now about orthogonal. Are you guys there who asked this question?
Yeah.
Yeah. Okay. So let's start from the scratch. Okay. First, understand what is orthogonal transformation. Okay. Uh, if we go by definition, then what does the definition say? That inner product of TV, right? Okay, and this should hold for all u and v belonging to V. This is what your definition for orthogonal transformation, right?
Yes.
Okay, but what does this basically means? It's saying. Hmm. Okay. Hmm. Let's say you are taking two vectors u and v, okay, and the angle between u and v is, let's say, theta. Okay, this is your angle, and after transformation you will get some different two vectors, right? After transformation, let's say your two vectors are here, okay, but if it is coming from an orthogonal transformation, then the angle between them will still be the same. Okay, the angle between them will still be the same. Okay, and the length of those vector will also be remains to be the same. Okay, that's what the orthogonal transformation does. The length and the angle between them will preserve in an orthogonal transformation. Okay, till now you got it?
Yes.
Yes.
Yes,
Okay.
sir.
Yeah. So one example we can take, we get the orthogonal transformation. Not okay. Here we have to find which of the following are orthogonal transformation or not. Okay. Let's take first T1. Okay. T1 is what? X comma y such that x plus y by root 2 comma x minus y by root 2. Okay. Now, if you check T of x1 comma y1, okay, with T1 of x2 comma y2, and it should be equal to inner product of x1 y1 with x2 y2, right?
Right. Right.
That's what the basic definition of orthogonal transformation say. So what will be the its image here? This x1 plus y1 by root 2 comma x1 minus y1 by root 2, okay, x2 plus y2 by root 2, inner product of these two should be equal to inner product of this. What will be the inner product of this? x1 x2 plus y1
Right.
y2,
Right.
right? Now if you see uh, 1 by root 2 will come out common from here, 1 by root 2 will come out from here, so it will be 1 by 2, right? And then it will be x1 plus y1 comma x1 minus y1, x2 plus y2 comma x2 minus y2. Okay, if you take the inner product, you will get x1 x2 plus y2 y1 x2 plus y1 y2 x1 x2 minus x1 y2 minus y1 x2 plus y1 y2, this whole divided by 1 by 2. x1 y2 x1 y2 cancel, y1 x2 y1 x2 cancel. Okay, so you'll get 1 by 2 2x1 x2 plus 2 y1 y2 y1 y2. Okay, and which is same as this, right? So this is
Yes, sir.
an orthogonal transformation.
This thing we get, like we got it, but
Yeah,
how this
yeah,
is like related to
hmm.
projection and all rotation
Yeah,
projection.
yeah. Hmm. So now the matrix of the orthogonal transformation is the orthogonal matrix. Okay, the matrix you will get from orthogonal transformation will be your orthogonal matrix. And there are other condition of orthogonal matrix are that it is a matrix first, it is a matrix of orthogonal transformation. Okay, and other are A transpose equal to A transpose A is equal to identity, right?
Mm. Yes.
Now this A transpose, let's take first this term. Okay, this implies that rows of A are orthonormal. How? Because let's take this. Okay, this is your A, R1, R2, R3, where R1 represent the first row, R2 represent second row, and R3 represent third row. Okay, what will be its transpose? This will be this, right? Correct? Till now any
Correct.
problem?
No.
No? No? the matrix you will get first row multiplied with first column r1 r1, first row second column r1 r2, first row third column. Okay, now if this is equal to your identity matrix, that means what? R1 R1, R2 R2, R3 R3, the inner product of them are coming out to be 1 while others to be 0. That means the rows of A are orthogonal to orthonormal to each other. Okay, so same thing, A transpose A will implies columns of A are orthonormal. Okay, any doubt till now?
Like if we found the dot product from itself, it should be one. Then it's on orthonormal. Like if we
Yeah, dot product of itself is 1 while with others it will be 0. Okay, then they are orthonormal. Okay, so A transpose A. But see, this case that A transpose equal to A transpose A equal to I. This case can only hold for a square matrix. Okay,
yeah.
because if you take your matrix like
Anyways, also
it is
identity matrix are only for the square one, right?
no see uh, even if you are do what will be the its transpose?
And
No,
this is
what
also
will
make a square matrix if you multiply both of them.
yeah, it's not necessary that the on multiplying you are getting square matrix. Okay, but
Why
see,
why it's not like it's 2 comma 3 and it's 3 comma 2? Then it will be two cross two, right?
yeah, no, I am telling like uh, it is not necessary that if the result is your square matrix then these two need to be your square
Yeah,
matrix.
yeah. That
Hmm. This is your 3 cross 2 and this is your 2 cross 3, so the matrix you will get here 3 cross 3. But see here columns are orthonormal, right?
right.
Correct. So you will get A transpose A to be I, but if you do A transpose, it will not be your I, right? You can try it. A transpose will not be I. Okay.
What is
So
my
this
A? This first
what
matrix,
A
right?
is, yeah. See, you can try A transpose. It means 1 by root 2 0, 1 by root 2 0 1 0, 1 by root 2 0 0 1, 1 by root 2 0. Okay, first row with first column,
That is
then
one
it will be first row with
zero
second column.
zero.
Oh, in case I guess we are getting here, we are getting, I guess. Oh, wait. Mm, are the rows are
Yeah, these columns are orthogonal and rows also.
how can rows are not orthogonal?
It's orthogonal, right?
Oh, see, we are doing A transpose A here. So because if this is our A, then we are doing A transpose A here. That's why we are getting.
Like if it was A into A transpose, then
Uh, yeah, A into A transpose will be this. Because this is our A, yeah, and this is our trans. Okay. Now if you do it, you will not get. Okay, you will get 1 by 2. See, at the start you're already getting 1 by 2, so it will not be our identity matrix. Okay. Before we were doing A transpose A. That's why we were getting.
to means A should be a square matrix for these.
Yeah, or if this condition, okay, for this condition that A transpose equal to A transpose A equal to I, if from both side it is equal, then this case only happen for square matrix. Okay.
Okay.
For rectangle matrix, one of the case will fail. Either it will, because see that it is a 3 cross 2 matrix, right? So columns are orthonormal, but the rows of A are not orthonormal, right? Correct?
How, sir? It's
The
orthonormal.
rows of A 1 by root 2 comma 0. What will be the norm of 1 by root 2 comma 0? What will be the its norm?
It's 1 by 2.
Root 2, right? Is
1
it
by
1?
root 2. Huh?
Is it 1? The norm of vector should be 1, right? In orthonormal.
You're saying orthonormal.
Yeah, I am saying orthonormal. Okay. Here our vectors will be orthonormal. Okay, that's what I am saying. The columns of A will be orthonormal and the rows of A will be orthonormal. Okay, got it?
Yes.
Okay.
Okay. So that matrix will be your orthogonal matrix. In our course, we are usually taking square matrix. Okay,
Mm.
and we all know what will be the determinant of A if A is your orthogonal matrix.
1 or minus
1.
1.
1 or minus 1.
Plus minus 1, right? Now, and what will be the inverse of A?
Mm.
It will be invertible, correct, but
Uh, inverse matrix. I am telling. Okay. See, what is inverse matrix? Inverse matrix is such that if you multiply A to be A inverse, you will get identity. That is what your inverse matrix is. Here, by multiplying it to its transpose, you are getting its identity, right? Correct? So your
Right.
inverse matrix is nothing but its transpose. Okay?
For orthogonal matrix, its transpose is
Yeah,
itself
it's inverse.
it's
Inverse.
inverse.
Okay?
Okay.
Hmm. So a matrix is orthogonal if only if its rows are orthonormal and its columns are orthonormal. Okay? See, orthonormal, not only orthogonal,
Okay.
orthonormal they should be. Okay? That means
Okay.
norm of each vector should be 1 and the dot product of vector with each other should be 0. So
Now,
it's all clear, right? Or any doubt?
no, it's clear till here.
Okay. Now comes the rotational part. Hmm. So first of all, before going to rotational, what is just the rotation term here basically mean? Mhm. Okay. Let's say this is my vector u. Okay. That and okay, this is my another vector v. Okay. U is making an angle phi with positive. Oh, U is making an angle phi. Okay. U is making an angle phi with positive x-axis. Remember that we always take our angle from positive x-axis, that is anti-clockwise. Okay, not like that. Okay, and this v here, okay, this is making an angle phi dash. Okay, by the term rotation you mean Okay, so if I am rotating these vectors, okay, by an angle theta, that means it is already making phi with x-axis before, but now it will make phi plus theta. Okay, and what will be this angle then?
Phi dash plus theta.
Yeah, phi dash plus theta. Okay, this is just by simple rotation terming. Okay, now
Sorry, can you tell me this again?
yeah, see, uh, we have two vector u and v. U is your making angle phi with positive x-axis, and v is your making phi dash with x-axis. Okay, and after if we rotate this vector by angle theta, then uh, this will be your angle phi plus theta, and we will make your angle phi dash plus theta. Okay, if you are rotating those vectors by an angle theta.
Okay, we are rotating both
Yeah. Okay,
with theta.
we are
Okay.
rotating. Hmm. Till now it's clear.
Yeah.
And uh, yeah, so if you have given that what changes will happen to the basis of in space with linear transformation, can we know the whole about linear transformation, right? Like if you have given what is happening to t of 1 0 and 0 1, you know what is your linear transformation, right? Correct.
No, I don't know.
Yeah. If you have given like t of 1 0 is 2 comma 3 and t of
Okay.
0 1 is 1 comma 2, then what will be your
Yes.
linear transformation? 2x plus y comma 3x plus 2y, right?
Yes, yes.
That thing you know, right?
Yes.
So mm, okay, let's say I am talking about here R2. Okay, this is your 1 comma 0, right? Here, correct?
Yes.
Is this okay? If I rotate this vector by an angle theta, yeah, okay, so here it will be right, and this is rotated by an angle theta. Okay, so this much trigonometry, I don't know if you know that we can represent it as cos theta comma sin theta. Okay, any unit
Okay.
vector we can represent as cos theta comma sin theta. Okay, and this is an unit vector 1 comma 0, so after rotating it by theta I can write it as cos theta comma sin theta. Okay, if you don't
Yes.
know, then you can memorize it, or after quiz 2 you can read it on Google, or like watch the videos on YouTube, like how we got like anything. Okay,
Is it because like it's under root of cos square plus sine square and cos square
yes,
theta plus sine
because
square theta is 1?
cos theta, yeah, cos theta comma sin theta, if any vector you will get, then
Unit
what will be it?
vectors, right? It's
Yeah,
cos square theta plus sine square theta
yeah,
under root.
because
That's
yeah, because the
it's 1.
norm of its vector will be 1, right?
Yeah, 1. Yeah.
Yeah.
Hmm.
Hmm. Okay, so any unit vector we can represent as cos theta comma sin theta. So that means what is happening to my 1 0? My t of 1 0 is becoming cos theta comma sin theta, right? Correct or
Yes.
not?
Yes, yes.
Now let's see
Then
what happened.
T of 0 1 also, like.
Yeah, but yeah, see, and yes, t of 0 1 here. Oh, one. Hmm. Let me use this. This vector here is your 0 comma 1, correct? Okay, this is your vector 0 comma 1. If I am going to rotate it with the same angle, okay, if I am going to rotate it with the same angle, now tell me in which quadrant it will go, first quadrant or second quadrant?
Second quadrant.
Right, it will go in second quadrant. Okay. Hmm. And now if we know this angle is 90, right, and here it is rotated as by theta, so it will be cos of 90 plus theta comma sine of 90 plus theta. Okay, from the same thing just as I told you that we
Yes,
can
yes,
represent any
yes.
unit vector in terms of cos theta comma sine theta. Here your angle will be 90 plus theta and 90 plus theta. Did you get it how I got 90 plus theta?
Yes, yes, 90.
Yes.
Okay, so that means
Like
what?
we are rotating that same vector 1 comma 0 in this direction. We can say also that.
Yeah, yeah, we are rotating both. Okay, I'm just
If I
representing
say
like one by
I
one.
rotate 1 comma 0 to 90 plus theta,
Okay, then that will also be like your
the
1 0
same,
and the same angle. Okay, the
yeah,
same angle you are following. Okay, then it will be like 180 plus theta.
like it's identical, we can say.
Hmm. Okay, because both changes are happen to at the same time. Okay, you are rotating both vectors with same angle. Okay, so what is cos 90 plus theta? Uh,
Cos 90 plus
base
theta is sine theta, right?
cos 90 plus theta is minus sine theta.
Yeah,
Sine
but
90 plus
because
theta is
cos is negative in that quadrant.
see, because it will go in second quadrant, and in second quadrant only cos and cosec has positive value. Every other will
Sine
have
and cosec is positive value.
cosec will take positive value, and every other will take negative value. Okay, so it will be minus sine theta, comma cos theta, and t of 10 we already found it that it was sine sorry cos theta, comma sine theta. So your uh, t of
So
xy will come from
why do we say that it preserves the angle and length? Length, I understand it. Nothing is
I am
happening
okay.
to it.
Okay, I am coming to that part only.
Okay,
Just
okay.
wait for a few minutes, okay? So t of x comma y. Okay, tell me what it will be. Cos theta x minus sine theta y sine theta x plus cos theta y. Okay, and the matrix we will got will be this, right? Cos theta minus sine theta sine theta cos theta. Okay, this is just the notation. Okay, till now did you got it? I just
Yes.
found the transformation and its matrix. I am taking both standard order basis for both domain and codomain here. Now, if you clearly observe the rows of this r theta, the rows of r theta, what? Cos theta comma minus sine theta and sine theta comma cos theta. What will be their inner product? Cos theta sine theta minus sine theta cos theta. That is 0, right? Correct?
Yes, so it's
And
orthogonal.
yeah, ortho and cos theta minus sine theta, what will be the norm of it?
Normal.
1,
Yes,
right?
one. Yeah, it's
Rows
orthonormal.
of this matrix. Rows of this matrix are what? Orthonormal.
Orthonormal. Yeah,
Same with the columns. Okay, columns are also orthonormal. Correct.
correct.
So as I told you, if any matrix has columns are orthonormal and rows are orthonormal, then what that matrix is?
Ortho,
Orthogonal.
orthogonal
Orthogonal.
matrix.
So your R theta is an orthogonal matrix. And your orthogonal matrix comes from what? Orthogonal transformation. Correct?
Okay.
Yes,
Correct. Orthogonal matrix comes from orthogonal transformation. So orthogonal transformation, as I already show you, it preserves length and angle. Okay, and that's why we also say that the flotation matrix also preserve length and angle. Okay, see in our course only this much you need to know about the rotation matrix and orthogonal matrix. Okay,
Like in
then now
R3 also we got some
yeah,
question.
okay, R in R3, yeah, it is on live on YouTube, right? I don't
yeah,
think
maybe
so
you
any.
can stop
Yeah,
recording.
we can stop that.
No, actually I have told sir about it. I am not the host. Yeah, I guess we can use GeoGebra still. Yeah.
Can you also cover one more thing like the kernel in terms of the projections? Range I understand, kernel I'm not getting, and W perp that thing.
Uh, what? Kernel of what?
I don't know, like in terms of this projection, like what kernel is like. In matrices, I understand, but in projections, what is kernel?
Is it used here in this
Indicate it is there.
kernel of
Yeah.
where? Can you show me? Can you tell me which question?
Uh, I don't remember now because madam actually she discussed in the class in the live session.
Yeah, let me check question.
Okay. If you find, I don't remember.
Also, I want to understand that W perp.
The orthogonal complement.
Tell me that also.
It's about to
Yeah, that
11:30.
is same. That is the same.
Yeah.
Like
See,
orthogonal
it's
complement is
it's just the orthogonal complement. See, the W curve is let's we just say, okay, the W curve is basically all set of vectors. Let's say if we have W set, okay, and this is your W, then W perp is basically all set of vectors which are perpendicular to this W vector. Okay, that means the orthogonal. Okay, that are
Then
the
why it is
ortho.
called as complementary? Okay, okay, okay.
Okay, so are you able to see my screen? No,
No.
no. Okay, so see, this one is your 3D. Okay, in 3D because we have like many direction. Okay, so in our course, we are only taking three directions. That is rotation along x-axis, rotation along y-axis, and rotation along z-axis. Okay. Now, if you see here, we are rotating this matrix. Okay, the matrix here. This is this only identity. Now, if I am going to rotate it along y-axis, see, this will be its image. Uh, okay. uh, just wait. Mm. Yeah. So are you able to see? If I am rotating it along y-axis, that's how it will rotate, right? The y coordinate will remain as it is. See the matrix here. Okay, see this matrix. The y coordinate will remain as it is, and only the change will happen in xy coordinate, sorry, xz coordinate. Okay, and the same thing will happen when if we rotate it along x-axis or z-axis. Okay, so uh, in R3, if we rotate along x-axis, okay, your x-axis will remain as it is, right? And your yz will rotate, and that will be your same this. Okay, for y-axis it will be this, 0 0 sine theta and cos theta, same as z-axis, cos theta minus sine theta, sine theta, cos theta, 0 0 1 0. Okay, only these three are given in our course. Okay, this is your rotation matrix. Yeah. Okay, so did you understand something
Yes, sir.
or not? Yeah.
Yes.
Okay,
Is there
and
anything which we
that,
should know?
no, for this course only these things are enough. Okay, the thing I told you, these are enough for you. Okay,
Okay, we'll go through VK tomorrow and
if you
then.
want, yeah,
So,
if you
so
want to learn more about,
like
yeah.
one question also I want to ask.
Hmm?
Like it's like wait, it's
Uh,
like projection of we have two subspaces like W1 and W2
okay.
of a vector space V.
Hmm.
Now the projection of W1 and W2
Okay.
from V to W1 and V to W2. Like PW1 is from V to W1 and PW2 is from V to W2.
Okay.
Now the statement is like PW1 plus PW2 is a projection from V to W1 plus W2. Then
Uh,
like ma'am
uh,
told in a
I guess it was in your practice assignment.
yeah, this was in also a practice assignment, but I didn't remember in which.
Okay, so yeah.
I think in
Okay.
projection it's there.
Okay.
How to like interpret these kind of questions in the exam?
Yeah, like we didn't. This question is
It's see, I understood that this one is a typical question and this is not easy to solve. Okay. So yeah, I guess it was question, this question, right? If PW1 and PW2 is a projection from V to W1 plus W2, this question, right?
Yes, this question
like
also.
how to like initiate this kind of question like
See, you have to see, it is what PW1 on PW2 plus PW1 of PW2. You have to use here the property of uh, projections and all. Okay, like I guess here what we did first, PW1 plus PW2 is a projection from V to W1 plus W2, PW1 plus PW2. What is this dot here? Is this dot
It's dot
product.
of PW1 of
It's dot
PW2.
product or
I don't think it's dot product. I think it's like composition kind of thing.
but PW1 will be your vector.
And how, I mean, I'm not getting how it is happening, what is happening. How come PW1 plus PW2 appears in the first?
Yeah.
Okay,
Like
see.
how do we multiply this in this
Okay,
form?
PW1 W2. Okay, projection of the one vector will be also okay. This one PW1 PW2. That means PW1 will be a projection from V to W1 and PW2 will be a projection from uh, V to W2. Okay. Hmm.
In the subspace of V, we get it W1 and W2. So the projection is happening in the same vector space. So like in the same vector space, the projection is like same will be the same, na? Same vector space.
Oh, wait.
Like till
PW1
here, I got it.
PW2. Okay, so it was a statement that is given. Okay, so see, it was the statement that is given, right? PW1 plus P, and it is the dot product. Okay, according
This
to
is
me,
dot product.
it is dot product because see, first of all, these are vectors. So how can the composition be different? Composition different between the what functions. See, because that what we are doing here, PW1, 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 PW2, PW2,
Yeah.
PW1. So it is
So
the dot product.
so maybe like is it like PW1 into PW1, it's PW1 square. So it is
Yeah,
same as PW1.
yeah, that is given in here. Okay,
But
Okay.
and
the
from
it's like it. I don't think it's a dot product now. And if it is dot product, then it will be like PW1 into PW2 plus PW2 into PW2.
that is
And
given. See the here. Are you able to see my cursor?
It's not defined, I think, the product.
Mm. Are you able to see PW1,
What?
PW1 that we are doing, right? Okay, session just like I guess in less than few hours. Okay,
okay.
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 Like after 14 hours, we are having a session.
And today also this I think there was no any old paper discussion session, and we saw at 8 p.m. there was no session, and suddenly
It was actually happening like that. No instructor was free today to take revision session. So instead of revision session, we switched it to PYQ session. I
Okay.
also get to inform like just 10 minutes ago, like 10 minutes before the session.
okay,
And in calendar it was showing like
Yeah,
2
one,
p.m.
because
yeah, one
the rest
PYQ
is
session. It was by
yeah.
mistake, right, in the calendar?
No, now if you see, only this link will show. Okay,
Yeah, yeah.
and
Okay.
actually, sir was updating the calendar, so that's why it was showing before.
Okay. We thought that we might miss one session.
Yeah.
No, okay.
Okay. Yeah.
Okay. Thank you,
So
sir.
we are
And
ending the
also,
session.
please consider that question next
Okay,
tomorrow.
this one, right?
Yeah,
Projection.
yeah.
Okay,
And I have
Yeah.
few more questions, but it's too late.
okay, yeah. After 14
Okay.
hours, we are meeting again. Okay.
Okay,
Yeah.
sir.
Yeah,
Yeah.
yeah.
Okay.
Thanks
Thank
for
you.
the
Bye bye. Good night.
yeah.
Yeah.
Thank
Bye.
you,
Good
sir.
night.
Thank you.
Yeah.